present you. So we are glad to have our next speaker, Kaveh Mousavand, from Queen's University in Canada, and he'll present us his work on the moduli spaces of quiver representations and an open conjecture. Please, go ahead.
Thank you very much for the introduction, as well as the opportunity to speak in this session. I understand that the way that I think and speak about my problems is slightly different from the language that I have been hearing in the past couple of talks. So I apologize if this seems a little bit out of the scope, but I'm going to make a very courageous promise and say that if you just give me 5 minutes, I state an open conjecture that only requires linear algebra at the undergraduate level. And that open conjecture, if I get the chance, I elaborate on how it relates to several active areas of research and what makes it interesting. So this is based on a joint work with Charles Paquette. And without further ado, I give you an outline of what the talk would be about. I begin with the conjecture. That is actually how I approach the problem we are going to discuss today. Then I outline the methodology, of course, in a very brief version. And finally, I present a little bit of comments regarding the significance and the novelty of the conjecture, as well as the reductive process that we have employed and some classes that we have verified the conjecture for. Henceforth, I stick to the notation and convention that I work over algebraically closed field, which is the setting that most of the speakers have talked about. I assume that A is always a basic connected finite dimensional K algebra. And please let me assure you that I can state whatever I say only about the setting of finite dimensional K algebras. But in order to have a nicer presentation, I introduced the condition A to be basic and connected. If you start from any finite dimensional algebra, you can reduce the problem to this setting. And finally, by mod of A, I refer to the module category of finitely generated left A modules. One simple observation, because A itself is a finite dimensional K algebra, every finitely generated module would be itself a finite dimensional vector space. So we can talk about the notion of vector space or dimension of the module, as well as the fact that I assume that A is basic. One good consequence of that is we can say the dimension of every module is the same as its length. And by length, I mean the length of composition series of the given module. So when I say length, you hear dimension as a vector space. There's no difference henceforth. And the objective is to pick up a finite dimensional algebra, A, select an integer D, and treat this scheme, which I mostly view it as a particular affine variety. That is only the scheme of all A modules whose dimension is the fixed integer D. What we want to look at are the connected components of this scheme or affine variety. And further, for each of the connected components, we want to analyze the irreducible components of that connected component. So this is what we are going to do in this talk. I only present two definitions, and then I state the conjecture. The first definition is a module M is called a brick, provided that the endomorphism algebra of M is trivial. Namely, every non-zero A homomorphism from M to M is invertible. These are the simplest type of indecomposables we can think about. Obviously, by definition, every brick is indecomposable. So these are even simpler than an arbitrary indecomposable A module. Then an algebra is called representation finite, or rep finite for short, if the module category that you're studying has only finitely many isoclasses of indecomposables. And analogously, we say A is break finite if the module category has only finitely many isoclasses of breaks. Henceforth, when I refer to modules, I mean always up to isoclasses. In the geometric setting, often the bricks are called Schur representations. Connections to root systems and algebraic geometry, so you may have come across this notion through the terminology of Schur representations. And every finite algebra is evidently break finite because every break is indecomposable by definition, a simple test. And but the converse is not true. In fact, you may have an algebra which admits only finitely many bricks, but it admits infinitely many indecomposables. So here is the difference, that for a rep infinite algebra, you may have only finitely many bricks. Just two very elementary observations. Now here comes the conjecture. The conjecture states that an algebra is brick infinite if and only if you can find an integer d such that the associated affine variety contains infinitely many non-isomorphic bricks. So what does that mean? It means that if we have infinitely many bricks, we can find a one-parameter family of bricks which are of the same length. For those who are acquainted with the Brauer-Thrall conjectures that appeared in 50s, 60s, and 70s, that kind of received a lot of attention, this may remind you of those conjectures, but I want to ensure you that it's not a verbatim translation of any of those. One side of the conjecture is obvious. If you have one parameter family of bricks of the same length, obviously you're brick infinite. But the converse has been the open side in the past 2 years. So I hope that in the first few minutes, I convinced you that the conjecture doesn't require anything beyond linear algebra, but seems to be a very interesting problem to treat. I'll hopefully tell you why. So a couple of remarks on this conjecture. It's called conjecture M because I was the one who conjectured this statement first, and it appeared in my preprint. I approached the conjecture through a very representation theoretical setting, which is called tau tilting theory. I'm not going to talk about it. And I phrase the conjecture in this language because it avoids the technicality of tau tilting theory. It simply employs linear algebra. I later give you a version which is more geometric. And further, it relates to the work of Chindris-Kinser and Weyman, who usually study representation theory from the more algebraic geometric perspective. So I need to provide the setting. The second section would be the methodology or the tools that relate the algebraic side to the geometric side. This consists of two fundamental theorems of Gabriel, both appeared in 70s. The first one states that if you pick up any arbitrary finite dimensional algebra, A, then you can find a unique quiver and an ideal, I, which is not necessarily unique, such that you can kind of represent your original algebra up to Morita equivalence as a quotient of a path algebra. I have not yet defined what a quiver is. I'm sure that a lot of you have come across that, but I remind you what a quiver is. And the quotient of a path algebra, I need to remind you what a path algebra is. So this, like the second version appearing in green, is the less formal language. It says if you want to study finite dimensional algebras, treat them as quotients of path algebras. Further, it goes one step ahead and it says, if you are given a quiver and an ideal with some properties, then there is actually an equivalence between two abelian categories. One being representations of the quiver subject to some relations, and the other side, the module category that you're interested in. So again, that's an indication that everything from the algebraic module category setting can be translated to a representation theoretical setting of quivers, quiver representations. The green version is also the less formal language that I present the theorem in. So reminder, a quiver is nothing but a directed graph. Quiver is a just fancy word to avoid the overuse of the term directed graph. Formally, it's a four-tuple consisting of a set of vertices, often denoted by Q0, set of arrows, Q1, and start of each arrow and end of each arrow. And path is defined in the most natural way. A path consists of a sequence of compatible arrows, such that if you go through arrow theta 1, it ends where theta 2 begins, and theta 2 ends where theta 3 begins, and so on and so forth. So that's called a path in a directed graph. And in all the talk, I assume that my quivers are finite, namely the set of vertices as well as the set of arrows are finite. So what is a path algebra? We start with the vector space structure of the algebra. The basis of this algebra consists of the paths that you constructed in your quiver. And you want to introduce the multiplication in this algebra, in this vector space, to make it an algebra. So you would say, if I multiply two arbitrary paths, they compose to a non-zero element provided the end of the first path is the beginning of the second. And otherwise, if they are not compatible, we cannot concatenate them, that would be zero. So then it comes the formal definition of a representation and the formal definition of the maps. But let me just tell you the final object when we treat representation of quivers. We want to construct an abelian category with some outstanding properties. So we define representations in the formal language on the slide, and the maps among them, again, formally defined over there. But instead of going through the terminology and notations, let me give you an example. So Q is a quiver with 4 vertices and 3 arrows, a directed graph. And a representation is nothing but associating finite dimensional vector spaces to each vertex, V1, V2, V3, V4. And maps, you additionally put linear maps between V1 and V2. And what are these linear maps? These are just finite size matrices. Because we're working with vector spaces, we only need to put matrices which fits the dimension of these vector spaces. So that is just one representation of this quiver, for example. The path algebra for that quiver is 9-dimensional, because if you compute all possible paths, you see that alpha composed with A composed with B is non-zero, A composed with C is non-zero, A itself is a generator, B itself, C itself, and 4 additional paths which are called lazy paths. Those are the paths that do not leave a vertex. They are gonna play the role of idempotence. So if you have another representation of the same quiver, which would be a bunch of vector spaces and similarly a bunch of linear maps between them, then you would define a map from the first representation M to the second representation N via a bunch of other linear maps from the vector spaces such that they satisfy the commutativity relation in the most natural way. So I want to just tell you that if we want to even impose some relations to the quiver, some further restrictions, the notion of representations and the maps go pretty much mutatis mutandis. I mean, verbatim, you can talk about the same thing. So as the result, you obtain an abelian category. You may not find it interesting in the first place if you are not from the representation theoretical background. But again, I remind you of the fundamental theorem of Gabriel. This language allowed us to translate every finite dimensional module to a representation of a quiver, subject possibly to relations, and also the equivalence of the calibers. On the other hand, we can talk about the geometric setting, in which sense we've previously talked about an affine variety mod of A and D, and we can further talk about like dimension vectors. Those are just tuples with Q0 many non-negative integers, and you collect all representations whose dimension vector is the given dimension vector C. And there would be a natural action of the general linear group. So as any other variety, we need an action, and here we act with a general linear group. So the action goes pretty smoothly because of the time constraint. I just remind you that the key point you need to pick up from this argument is that the orbits of this action would be the same as the isoclasses of A modules of the fixed dimension vector. Now, how can I reform or reformulate my conjecture? I can state it in the following version. An algebra A is brick finite. Remember, it's a linear algebra version. It's brick finite if and only if you can find it's brick finite if and only if you pick up any dimension vector, you look at the irreducible components of the affine variety of modules of that fixed dimension vector, and there is at most one orbit of bricks in every irreducible component. So it puts, if the conjecture holds, it puts a very strong condition on the behavior of irreducible components of all module varieties over that algebra. That property had been treated from a different perspective, of course not the conjecture, but that property that appears in blue had been treated by Chindris-Kinser-Weyman. So I want to introduce the final part, and I understand that I'm approaching the end of my time, so I go a little bit faster. Here's the conjecture that we saw in the more geometric language. We want to reduce this conjecture to a particular family of algebras. The way that I treat it is we introduce the notion of minimal brick infinite algebras as those algebras which have infinitely many bricks, obviously up to isomorphism class, infinitely many isoclasses of bricks. But if you take any quotient of that, any proper quotient of them, the resulting quotient would be brick finite. Again, this resembles the notion of minimal representation in infinite algebras, but I'm not going to go through the details. So the first theorem that I want to present here is, in order to verify the conjecture with Charles Paquette, we prove that it's enough to prove the conjecture for those minimal brick infinite algebras over which almost every brick is faithful. By almost every, I mean all but finitely many bricks. So from that whole generality, you reduce to a particular subfamily over which the modules, the bricks that you're interested in behave in a particular way. And then, due to the time constraint, I very briefly summarize the second result. There is a very important family of algebras called biserial algebras. They were introduced by Fuller formally. And those are the algebras for which every left and right indecomposable projective has the property that you can write the rad of that indecomposable projective as sum of two uniserials whose intersection satisfies the properties on this slide. Biserial algebras are interesting because they have applications in cluster algebra, representation theory, homological mirror symmetry, stability conditions, and such and such. Time constraint doesn't allow me to go further. But so if I finish, it would be the theorem appearing at the end, which says we have successfully verified the conjecture for all biserial algebras. Namely, the statement is the one that you see. It's Brigg finite if and only if for every dimension vector and every irreducible component, there is at most one orbit of Briggs. I didn't have time to go through a lot of comments, which are just left on the final slide. I hope I can upload the slides so you can have a look at them. But to summarize and finish, if we settle this conjecture, on the one hand, we have at the algebraic setting of tau tilting theory. On the other hand, we have the geometric setting of module varieties. And in between, we have stability conditions, lattice theory, combinatorics, and so on. Therefore, the conjecture seems to be of significance, provided which domain you select to approach it. Thank you very much for your attention, and once again for the opportunity.
Thank you, Kaveh.